If you need a moment to reread the problem, go ahead and pause the video and do so. We have two different legs of the journey. In the pink, we can see that the car is traveling 30 kilometers per hour for a distance of 40 kilometers. And then in green, it's traveling 60 kilometers per hour for that same distance of 40 kilometers. And in part A, we are asked to compute the average velocity of the car during the full 80 kilometer trip. Now, one thing you do not want to do is simply add 30 and 60 and divide by 2. That would be a very common mistake to try to find an average velocity. The reason we can't do that is because they are traveling at those velocities for different periods of time. And so we need to find another way of computing the average velocity. And what we're going to need to do is actually figure out the time involved for these legs of the journey. Now, we know that because the average velocity for this full trip is going to have to equal the total displacement, which is pretty easy to find. If you look at the diagram, the total displacement is simply 80 kilometers because of the straight line motion of this automobile, and then divided by the time. That's the definition of the average velocity, but it's the time that we need to figure out in order for us to solve this problem. And so we have listed the kinematics formulas on the left side here. Notice that the acceleration of the car is 0 in both cases, because for both legs of the journey, the car is traveling at a nice constant velocity. So acceleration is 0. That's going to be useful to us. We're looking for time in this case, and perhaps the easiest equation to use would be this second equation right here, because if you look at that equation carefully, consider the fact that the acceleration is 0, which would knock out this entire term right here. So for example, for the first leg of the journey, we could write that the delta x, which is equivalent to this x minus x naught, that delta x would equal the initial velocity multiplied by the time. And then to solve for the time, we would just divide both sides of that equation by the initial velocity. So we have delta x divided by the initial velocity is going to equal the time. We're going to call that t1 because that's for the first leg of the journey. We'll have the same term or the same equation for the second leg of the journey. So for the first leg, we'll go ahead and plug in the known values. Again, we have 40 kilometers for the displacement, and then divided by 30. Oh, I put a subscript 2 there. Excuse me. That should be a subscript 1. And so the initial velocity for the first leg was 30 kilometers per hour. That's going to give us t1. We'll do something similar for t2. And so we compute these times for t1. We're going to get about 1.33 hours for t1. And for t2, we're going to have 0.667 hours. And so now it's time for us to calculate this average velocity. Remember, the average velocity is the total displacement. Look at the diagram again. You can see the total displacement is going to be 80 kilometers for this straight line motion. It's 40 plus 40. So we have 80 kilometers in total displacement divided by the total time. For that total time, we're going to have to add the 1.33 hours plus the 0.667 hours. Now, of course, we could simplify that total time. If we add those together, we're simply going to get 2 hours. So we have 80 kilometers divided by 2 hours, and that's going to work out to 40 kilometers per hour. That is the correct answer to part A of the problem. That is the average velocity of this car. Now, in part B, we are asked for the average speed. Now that's interesting because average speed has a slightly different formula. We can symbolize average speed by doing v bar with an absolute value. And average speed is going to be the total distance, not displacement, total distance divided by total time. But the thing is, in this case, the car is moving in a straight line or along a straight road. It says that right here. So from, the first point to the last point, it traveled 80 kilometers. It's a straight line displacement, and therefore the distance is also going to be 80 kilometers. We divide that by the total time of 2 hours, and we get the same answer. It's going to be 40 kilometers per hour. So just notice that when you're moving along a straight line, that the average speed and the magnitude of the average velocity are going to be the same, and that's for straight line motion. Now in part C, we have to graph the position versus time and indicate how the average velocity is found on the graph. We'll scoot down here and do that. So we have made a horizontal scale of time and a vertical scale, or vertical axis, I should say, of the change in position. The car presumably starts at a position of 0, and then it travels a time of 1.33 hours. So that would be the red part of its journey. We computed 1.33 hours for a distance/displacement of 40 kilometers. And then for the second leg, it traveled 0.667 hours, bringing it up to a total time of 2 hours and a total distance/displacement of 80 kilometers. Now, what actually would represent the average velocity on a graph would be the slope of the line from where the car started, we could call that the initial position, to where the car ended, which would be its final position overall. You can see that if we connect the initial and final positions, we have that dashed line right there. If you find the slope of that dashed line, you would get the average velocity. We can go ahead and do that just to sort of confirm our answer. Notice the initial coordinate would be 0, 0, and the final coordinate is 280. So traditionally calculating slope, we would take the second y-coordinate, subtract the first y-coordinate, and then put that over the second x-coordinate subtracted by the first x-coordinate. So basically you're just doing a change in y over a change in x. And when you compute that, lo and behold, you do get 40 kilometers per hour. So the slope of that dashed line could also be used to calculate the average velocity of this automobile. We will stop.